Okay, let's move now to the practical part of this course. We will try to simulate compartmental models in order to verify the various insights that we saw during the course. To simulate compartmental models, we need to use a class of algorithms called ODE solvers. ODE means ordinary differential equations. We need these algorithms because it's very hard to solve analytically these models. That analytically means just by paper and pen. And even the most simple model needs to, it's exponentially difficult to solve analytically. So we need the computer algorithms for this. Just as an example, I will show you the algorithm of the most simple of these ODE solvers, the so-called Euler method, just to give you insight of what these algorithms do. So we need, first of all, we need to choose a small time interval in which we want to solve our model. And then we need to choose the initial conditions for our simulation. So in this case, we simulate a population of 1,000 individuals, of which 999 are susceptible, 0 are immune, and then we insert just one infected case. Then we need, of course, the parameter values of the model, our usual beta and gamma. Then the algorithm is pretty simple. We start from the condition of the model at a certain time point, so S at time -1, I at time -1, R at time -1, and then we add the increase of the change in number of individuals in each compartment, using the usual SIR formula. So for the number of susceptible, we just need to decrease an amount of cases given by lambda, that is beta by I over n, multiplied by the number of susceptibles. Then we add these cases to the infected compartment, and we remove those that recover, and then we add those that recover to the recovered compartment. Okay, this is quite simple to code up manually, but the results are far from perfect. Depending on how large is the time interval that we are considering, then there is an exponentially increasing error. But don't worry, because no one used Euler method anymore, because there are far more advanced algorithms at the moment. We will see now how to implement these models using R, which is a programming language which is much used in statistics and simulations. For this course, I assume that you have some basic knowledge of R, because going into the basics will take too much time. The central point of our simulation will be the package DESOLVE, which is a suite of differential equation solvers. So first of all, let's start setting up our workspace, that is loading all the functions that we need to work. We will use mostly 4 packages, that is DESOLVE for solving differential equations, dplyr that allows us to easily manipulate data, tidyr also used to manipulate data, and then ggplot2, which is used for plotting. We want to solve a very simple SIR model at the moment with, for example, beta equal to 1, so one case, one efficacious contact per day, and gamma equal to 1/8. And you can see below the diagram of the model. Just as a note, also this diagram is created using R, using the diagrammer package. So the input of our models, as we saw before, are the initial conditions. In this case, we have an SIR model, so we need 3 compartments. We are simulating a population of 1 million, in which we insert just one infectious case. Then we have our parameters, beta and gamma, as we saw before. And then our time points. In this case, we are using a day time interval, and we want to follow the simulation for 60 days. To do this, we need to define a vector of 60 days, from 1 to 60. Let's now look at the code that allows us to implement the SIR model. This is the central part of our simulation. in which in this function we define a programmatic equivalent of the SIR model. This first line here allows us to transform the arguments of these functions in a way so that we can access them directly. If we didn't use this syntactical trick, then we will need to write every time state square brackets state square brackets I state square bracket R. And also for the parameters, we will need to use parameters square bracket beta, parameters square brackets gamma, and so on. To make it easier to write the code, we can use with in order to access the variables inside this object directly. As you may notice, this function take as input the state of the model at each time point, the parameters which are fixed, and then also the time point that is being evaluated. This function will be then passed to the other solver, and it will be run in a loop for each time point. So once we have our variables, we need to compute n, which, as we saw in the previous lesson, needs to be the sum of all compartments, because we cannot leave any loose end, otherwise the model will fail. So the sum of these compartments will always need to be equal to n. Then we can define our lambda, which is, as we know, beta multiplied by the prevalence, I over n. And then we can define our differential equation, that is the changes in time of each compartment. So for the susceptible compartment, the change is minus lambda by s. For the infectious compartment, is lambda by s minus gamma by I. And for the recovered and immune compartment is gamma by I. It's the usual SIR formula. Finally, we need to return this the differential steps into a list. We need to use list and then pass as argument to the list a vector with all the results. This is the kind of syntax required by all the solvers into the DESolve package. Then we can finally run our simulation. As we said before, we will use the DESolve package and specifically the ODE function. The ODE function will use by default an algorithm called LSODA, linear solver of ODE algorithms, which is quite smarter than the Euler algorithm. As argument to this function, we need to pass the initial conditions, the time points, the model that we defined in the previous function, and the parameter. And here you can see the kind of output that we can expect. As a small notice, notice that we use sDataFrame because the output of the ODE it's a matrix, but it's much easier to work with data frames in R, so we convert the matrix into data frame, and this is the output. You may notice that we can observe fraction of people changing in time, because as we said in the previous lessons, compartmental models are based on the so-called mass action effects, and they work with the fraction of people, which if you have a small population can create quite large biases, but if you have a large population, like in this case 1 million, then on average we won't see much biases. Finally, we want to visualize the results. For this purpose, we will use the package ggplot2, which I suggest you to learn about, since it's very useful for making professional-looking plots. We want to incorporate our plotting function, our plotting code into a function so that we can reuse it every time without rewriting all the code. So before plotting, we need to transform the data using the pivot longer function into the tidyr package. What does this function do? It takes a wide format data frame like this one, in which you have a column for each compartment, into a long format database in which we will have just two columns, one with the compartment, so we have SIR, 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 and then a value column with the value for each compartment. So values for S, value for I, value for R, then again value for S, repeated. But we want to retain the time variable as it is. Therefore, we tell the function to exclude the time variable from this transformation. Then we need just to choose some names for the new columns that we are creating. Either you can leave the default names, or you can put your own. In this case, I put comps for compartment and value for the values. Then we want to pass the results of this function to ggplot. Instead of saving the result in a variable and then calling the variable into ggplot, we can use some new syntax operators called the pipe operator, which allows us to join function in order that the output of a previous function became the first argument of the subsequent function. It's just a way to save writing and typing. In this case, actually, it doesn't change much because we have just one intermediate step. But when you have multiple steps, one after the other, it makes the code quite more clear to read. So how does it work, the ggplot library? First of all, we need to set up the plot with the function ggplot. This function takes as first argument the data which we passed using the pipe operator. Notice that this pipe operator is quite new, so you need the R version higher than 4.1. Or if you have older R, you can use this other kind of pipe operator, which is defined into the dplyr package. Now instead it's part of R itself. So the ggplot take as first argument the data, then as second argument the so-called aesthetics. That is, we want to assign a variable to each parameter of the plot. So for the x-axis we use the time, for the y-axis we use the values computed by the simulation, and then we also want to have different lines for each compartment with a different color. ggplot is quite smart, so if we use color equal to comps, it will automatically create different lines, choosing automatically the color, a different color for each line. Notice that both here and in ggplot, we are directly accessing the column's name. This is called a tidy evaluation mechanism, which allows some function to access directly the column, the variables into the data frame that we pass to them. So once we set up the plot, working with ggplot is quite easy. We just need to add graphic layers. In this case, I just add a line layer, but I could add also points. I could add histogram. I could add. There's a huge number of possible layers, and they just stack one over the other. So if I add a line and then a point, it means that the point will be plotted above the line. If I do the opposite, then it means that the line will be plotted above the points. Then I add some extra theming, because the default theme of ggplot is not very nice in my opinion. But the ggplot package offers you a number of extra themes that you can use. I usually use the theme minimal because it's quite clear, it doesn't have any extra color, so it's much readable. And then we can define labels in our plot. So we can have a label for each graphic parameter. So one for the x-axis, population for the y-axis, and also compartments for the colors. If we don't use this function, the names will be just the name of the columns that we use setting up the plot. Finally, we can run our plot. And this is the output. As you can see, this is a pretty typical kind of output for a SIR model, in which we have the prevalence that increases, have a peak and then start to decreases, which is accompanied by a constant decrease in the number of susceptible and then a constant increase in the number of immune in the population. Compliments, you have just drawn your first SIR model. Okay, now that we have in place the framework, 1 second that I drink a little bit of water. Now that we have the framework in place, let's start making some experiments. So we saw in the previous lessons that if R0 is below 1, then we cannot have an outbreak. Let's try this out. Let's create a new simulation with the same parameters. Sorry, not with the same parameters, with the parameters in order to have R0, which is more or less 60%, 65%, 0.65. And let's have an initial condition in order to have an imaginary population in which half of the people is susceptible, and then suddenly we have the same amount of people that immediately gets infectious. Of course, this is not possible in reality, but it's just to create an extreme situation to show what having R0 below 1 produce. Then the rest of the code is the same. We produce our simulation and we plot it. What happens? We can see that even with such a big amount of infectious people, if the parameters produce an R0 that is below 1, we won't have an outbreak. What does it mean not to have an outbreak? It means that the prevalence of the population will never be higher than the initial conditions. It will always be lower. And so we observe that as the simulation starts, the number of infections gets lower and lower. Of course, we have some people that get infected and therefore also get immune. But overall, the prevalence is always lower because more people recover than the people that get infected at each time point. This is a nice example that shows how the theory then transforms into something practical that we can observe. Let's make another example. This time we will investigate the herd immunity threshold. As we said before, if we have an epidemic with R0 above 1, we should see an outbreak. But if there is already some immunity in the population and this level of immunity is above the herd immunity threshold, we should expect not to have the outbreak, even if the R0 is above 1. Let's see how can we simulate this situation. So let's choose a set of parameters in order to have R0 equals to 8, which is fairly high. And we can extract R0 in this way, doing simply parameters beta above parameters gamma. As you can notice here that I use the asVector function because the parameter object is a named vector, and if we don't want to use asVector function, also R0 will be a named vector. Oddly will be a vector which name is beta, which can create some mess with the rest of the code. So in this way, using asVector, we assure that R0 is just a number and there is no name associated to it. From the R0, we can estimate the immunity threshold, as we know, which as we know is 1 minus 1 over R0, which is pretty simple. So let's create our simulation. We will make two different simulations. One in which we have a level of immunity which is exactly at the herd immunity threshold. So let's start. We can create a population of 1 million individuals, and then we remove 100,000 individuals, which will be the infectious introduced cases. We create an initial condition in this way. We create a number of immune people which is equal to the immunity threshold multiplied by the full population. Then we have a number of susceptible individuals, which is n minus r, which is again the immunity threshold multiplied by n. And then we have this initial infectious cases, which are 100,000. I put 100,000 in order to show how the effect of the immunity threshold, even with a large amount of initial infected cases. Then we have a second simulation. In this simulation, we have a level of immune which is slightly lower than the immunity threshold, 90% of the immunity threshold. And the susceptible are constructed in the same way as before. So the total population minus the immune. In this case, we will just introduce one infectious cases. Again, these are extreme examples to show how the theory is then confirmed by the simulation. The code is quite long, so I needed to split into different multiple slides. Let's set up our time interval. In this case, we need a slightly longer observation time, so 200 days. And let's create the two simulations. So the simulation in which the level of immune is at the level of the immunity threshold, and the simulation in which the level of immune is below the immunity threshold. The code is always the same. Once we created our simulations as data frames, we can bind them by row. That is, put one data frame on top of the other. We can use the bind rows function for this. But we also want to mark the two simulated data sets in order to recognize them. So we can add an extra variable, which we can call model, which define from which simulation the data comes from. So one for the population at the immunity threshold, and one with the population below the immunity threshold. We can use the mutate command from dplyr to modify data frames on the fly. Here I used the dplyr version of the piping operator, but we could have used also the native R version. It's just because I'm used to use this operator since I use it since many years. Then we need again to plot our results. We cannot use the previous function because we need to modify it a bit in order to take into account that we have two simulations in the same plot. And this code is the same as before, apart from two lines. This one, in which apart from removing time from the transformation, we also remove the model variable because we want to keep it separated. And we can do this by using a vector with the name of these columns and added minus above. Or we could have used a vector with minus time and minus model. It's totally the same. And then the other extra line is phased wrap, which allow to split up a plot according to some variable. This means that we want to have two different plots for each model. And this is the output. We can observe that even with a high number of initial infectious cases, the epidemic dies off anyway, because the number of immune is above or equal to the immunity threshold of the population. The immunity threshold for R naught of 8 is 87.5. Instead, if the level of immune is slightly below the immunity threshold, even one case can create an epidemic. Okay, it's a small epidemic, but still it's an epidemic. Finally, let's see a slightly more advanced example in which we also introduce demographics into our models. We will introduce a mortality of birth rate. We will assume that they are the same for simplicity, which equate to a lifespan of 80 years in the population. So we need, in order to make the visualization of the results more easily, I choose some parameters that again, and that create a simulation which is easier to visualize. So I choose a population which is 10,000 inhabitants, and I introduce one infected case. In order to make the simulation easier, I used months as a time span, not days or years. And so I simulated that each individual has 60 efficacious contacts per month, and that the disease is still 8 days long. But since we are working with months, I need to divide 8 by 30 days. And the lifespan is 80 years, but since we are working with month, I need to multiply it by 12. I use this example with month also because it's a way to show you how to modify, how changing the time definition requires also to change all the variables in order to take it into account. For example, I could have just also write here 2 by 30 to say that there are 2 efficacious contacts per day. We want to follow the the simulation for 100,000 months because we want to show the oscillations that we talked about in the lessons about demographics. So here is how the SIR model gets modified to include demographics. So this part stays the same. We have the total population, and then we have our lambda. Sorry. Okay. And but then we need to modify our differential equations. In addition to the classic SIR model components, so that is minus lambda s minus gamma I, blah, blah, blah. We need to add the birth rate, which is mu multiplied by the whole population. And we need to remove individuals according to the death rate. So we multiply S by mu, I by mu, and R by mu. I think the logic is easier to understand because every time a person is born, it is automatically susceptible. So we have a birth rate for the whole population, and we put the newborns into the susceptible category. And then we remove the people that die from the population in every compartment. We assume the same mortality rate for every compartment. So this is a natural mortality, not infection-related mortality. And then we return the results in the usual way. Finally, we run the simulation. This part of the course is the same. We just added a transformation in order to change months into years. So we make time, which is month, divided by 12. And then we want to compute some of the relevant statistics of the epidemic. So we can compute the usual closed population R0, which is beta over gamma. But we may be interested. We also need the R0 adjusted for the mortality rate, which is beta over gamma plus mu, because as you may remember, the infectious period it gets a little bit shorter because people may die out before recovering. We will see that the impact with this parameter is very low. Given that we have the R0 demographic, the demographic R0, we can estimate the average age of first infection, which as you may remember, is 1 over mu multiplied by R0 minus 1. And once we have the age of first infection, we can also estimate the periodicity of the oscillations in our population, which, if you remember, is 2 multiplied by p Greek, multiplied by the square root of age of infection, multiplied by the expected length of survival, which is gamma plus mu. Again, since we are working with months, we need to transform these parameters into years. So we just need to do to divide by 12, both of them, and then we can plot the results. This part of the code is the same because we created our own function, but we need to modify the output in order to take into account some difference in this model. ggplot is nice because you can just add elements that can overwrite the elements from before. So we want to add a fastest rep in order to have a different plot for each component. And each plot will have a different scale on the y-axis. This is useful because we will see that the number of infectious cases is much smaller than the other two compartments. And if we don't do this, it will be very hard to visualize the repeated epidemics. And then by using xlab years, we are overwriting the x-axis label, which was by default days. And these are the results. So the expected R0 is 16 in the closed population, but if we consider demographic as expected is slightly lower. In this case, much doesn't change much because we have this is the last 8 days, and expected life duration of 80 years. So this 80 years won't impact much on over 8 days. But for example, if we consider disease with a very long infectious period like tuberculosis, in which 1/gamma is counted in years, then we could see that the demographic R0 is much lower than the closed population R0. From the R0 we can compute the age of infection, which for such a high R0 is quite low, 5 years of age, and the periodicity, which is 8 years. And here you can see the output. As we saw before in the lesson, we have a so-called periodic behavior, in which we have these spikes, which are the outbreak, that then almost disappear, and then they repeat with a certain periodicity. But when they repeat, they are smaller and smaller in prevalence, in maximum prevalence. And the same is for the immune compartment and the susceptible compartment. What happens, as we talked before during the demographics lesson, is that we have an initial outbreak that create a certain number of immune in the population, almost 100%, but never 100%. And then, since there are no susceptibles anymore, the epidemic dies out. But as new individuals are born into the population, there are enough susceptible to create a new outbreak, which again make the population almost all immune, and then so the epidemic dies out, and then it reappears, and so on, so on, so on.